X-ray crystallography is a means or a tool that we use in order to analyze the structure of crystals, especially metals and ionic compounds. Although in this part of your syllabus we just focus on metals, there are crystalline lattice, and we like to know how they are laid, the atoms within. This is a picture of a ionic compound, sodium chloride, that I have. What any crystal lattice, whether your ionic or metallic, contains is repeating unit cells. Those are the smallest repeating units. In this case, they are cubes. Actually, this here, all we study are cubes. So these cubes are being repeated, and they are known as unit cells. So we have these cubes involved. Now there are a few terminologies associated with unit cells. The first one is coordination number, and it's number of atoms that the atom under study is in contact with. For example, if I go after this red sodium ion here, it is in contact with 6 more, and that's its coordination number. They are 1, 2, 3, fourth one back of the plane, and then there is one on top, one below. So there are 6 atoms in contact. So the sodium within sodium chloride has 6 coordination number. We worry about unit cells eventually, but let's concentrate on X-ray crystallography. Then again, we are going to give you limited information. We're not going to study its technology, or we're not going to use the calculations as how the equations are derived. Those are for physics students. So what we use is we use real X-rays. They have wavelengths that they come and they attack the crystal. If they hit the atoms in phase, if we have 2 of them, they are going to come out in phase, and this is what we study. So if that's the case, the incident light comes in, and then the diffraction we are going to study. And a father and son, actually, by last name Bragg, they came up with this equation to relate d, which we are interested. D is the distance of each of these lattices, the sides of the cube or the unit cells that we like to find out. To a lambda is the wavelength of the incident light, the X-ray, and the angle theta, that's important. If the theta is not in phase, your interactions actually cancel each other out. So angle of incident and the plane of the crystal is theta, and of course D is the most important information that pops out from this equation, which is the distance or the side of each of the unit cells. Now n is an integer, it's 1, 2, or 3. We only study n equal 1 for sake of simplicity, so every time you apply this equation, just put 1 for n, and that's first order diffraction pattern, but we're not going to get into the technicality of it. Just remember that to put 1 every time you have to use Bragg's equation. Now let's just apply that to a problem. So we are going to apply Bragg's equation to a problem. You have an X-ray wavelength at 154 picometers that was diffracted at an angle of 14.17 degrees. Then again, assume n equal 1. What is the distance? What is that d for each side of this unit cell? So let's just put Bragg's equation, which was n times lambda, the wavelength, is equal to times the distance of the sides of the block, unit cell, times sine theta. Now all we have to do is plug in. Of course, you have to respect the units. So the first thing I'm going to do is go after lambda and convert it to centimeters. Knowing this information, 1 picometer is actually 10 to minus 12 meters. But also 1 picometer is equal to 10 to minus 10 centimeter. We usually want it in centimeters, so I prefer if you remember the second relationship. So all I have to do is say if lambda is 154 picometers, it should equal to 154 times 10 to power of negative 10 centimeters. Now I'm ready. I like to find out d, so let me just rearrange my equation and say d is nothing but n times lambda divided by 2 times sine of that incident angle, theta, N is always 1 for us in chemistry. IB times lambda, which was 154 times 10 to minus 10 centimeters, divided by 2 sine of 14.17. Now plug it in your calculator. What I calculated was 314.5 times 10 to minus 10 centimeter. If this is 3 significant figures, I'm going to write this as 3 significant figures as 3.14 times 10 to minus 8 centimeter, and that's the side of each cube. This is my D that I was interested. So if this is the repeating units are cubes like this, now we just simply have calculated the side of each of these cubes that my atoms are within it. So we just calculated the D. D is also this side. It's also your width. So this is also D, which was 3.14 times 10 to minus 8 centimeters. Now this is the unit that contains my atoms. So if there are one atom in each corner, the atoms are going to take place like this, and they go on. So this is how the atoms are packing this unit cell. We worry about that later, but Bragg's equation is extremely useful. X-ray crystallography is extremely useful because now you can calculate dimension of the unit cells, eventually the volume. Just remember the volume of the unit cell. Since it's a cube, it's side times side times side, which is D cubed. In this case is 3.14 times 10 to minus 8 centimeter cubed. And finally you can calculate density of pure metals, and that's our objective, which I'm going to get into it on next slide.